Hello everyone, my name is Iucanaron. I'm a master student in the Department of Data Science at SOTEC. So today I'm will present the paper titled Agriculture of Future Bright Combination Forecasting with Whole Process Interpretable Method. And this paper is published in 2025 in the Applied Soft Computing journal. So now let's go through about the introduction and research problem. What is the problem here? So about the agriculture of future price are tricky. The noises affected by policies, international market, geopolitical risk, and so on. So in practical, they want three things at the same time. So for the first, the high prediction accuracy, and the second is the stable error. They don't want the big crash in the performance. And the third is interpretability. They want to know why the model predict a certain price. So existing model usually give us a part of this. Single model are unstable when the market regime change. Ansible may be more accurate, but the whys are often a black box, and the interpretability is often done only at the feature level, not for the whole pipeline. So this paper is trying to design a framework that balance accuracy, stability, and explainability all together. To position the paper, let me very quickly connect the related word. So in the paper they talk about three parts of the relative word. The first one is traditional AI-based and the hybrid model. So the first one is about traditional time series model like the ARIMA or the graph simple and interpretable, but they mainly capture the linear dynamics and have trouble with the strong nonlinear effect. And about the AI-based models such as the LSTMS, CNN, or the transformer handle nonlinearity and the long-term dependent, but they expensive, sometimes unstable, and it's very hard to interpret. And for the hybrid model, they combine with the several model to improve the robustness, but they are often just the erect or stuck model without the clear explaining for the how the whys are choosing or why the interval behave in the certain way. So now let me talk about the contribution. So for the main of the contribution of the paper, they found it. There are too many. So let's talk about the first. They build the two-stage feature engineering and selection pipeline. They start with the many constructed and the statistical feature, then use the motor information to get the top 10, and finally apply XGBoost with the soft value to keep only 4 core features for each dataset. And the second, they build a ensemble for the 3 of the model. Here there are 3. And the third, they insert the motorly using the whys, and they use the reinforcement called MCEORL to find the why that minimize 2 objects. That's one is the MAPE and errors variance. And the final, they design the whole process interpretability framework using the SHAP for the global feature important, LIME for the local case by case explanation, and the LRP for the internal layer wise relevance. They also plug the prediction into the simple trading strategy to check if the model is practically useful or not just good. on error metric. So this slide shows the whole pipeline of the paper. We think that it has 3 big steps. So on the left side, we start with the raw data. Domestic future price, international agricultural price, WIT, cultures, and geopolitical rice index, and the trading value. So the first author creates, there are many new feature. They add subtract, multiply, and divide those variable, and also calculate the statistic like the min max variables over the source window. And they give a lot of the feature of set of the 52 feature of the China and 30 for the US corn. Because there are too many, they do the step 2, the feature selection. The first, they match information to pick the top feature that relates most of to the price. And the second, they use the XGBoost with the SHAP value to choose the 4 final of the 4 core feature. And the step 2 is the SAS model wise optimization. So for this step, it is in the middle part. They use those 4 features they put into the 3 different model. So for the X model, we train with the separately on the training data. Then they use the to decide how wise to give each model in the ensemble. And for that, they also use the reinforcement learning version of the Charles evolution optimizations algorithm. So the reason that they use about the reinforcement learning here, they want to make the MAPE small with the high accuracy and make the errors variance small also with the stable prediction. And for the stage 3, they are the forecasting and the interpretability trading. So on the right side, they compute the final forecast as the y sum of the 3 model, and they evaluate the performance use the MAPE, MAE, and the OMS, and compare with the another model. About the dataset, author use 3 weekly future dataset. First, they use the Chinese soybean. It's about 541 points. Chinese corn about 572 points, and US corn about 543 points. And they also use the key driver usage in modeling. That we can see I'm right here for of the model key driver that help for the modeling the model. So now for this slide is the feature engineering. So for the step A, it's the feature construction. So starting from those original driver, they create the combined feature using the mathematics between the original driver. And the next one, the statistical feature like the min and max over the source moving window. As the result, they get the 52 dimensional feature space for the Chinese dataset, and the 30 dimension for the US corn. And for the step B, the feature selection have 2 layers. So for the first is motor information to rank all feature by the relationship with the target price and keep the top 10 this ranking to show it's in the picture. And also they fit with the XGBoost model and compute with the SHAP value to see which of the 10 actually contribute the most. And After this process, only the 4 features per dataset remain as the input to the deep model. And for this one, before the building Ansible, they test with the library of the model on the validate set of the Chinese source bin, GRU, CNNs, LSTM, transformer, and so on. So in the table 2, they shows that KAN-BiLSTM and Attention-LSTM and the BPNN give the best validation performance in the term of the MAPE, ME, and RMSE. So the idea is instead of the guessing which single agriculture is the best, they keep the top 3 and let the ensemble writing algorithm decide how to combine them. Let me explain about the structure of the KAN-BiLSTM from this picture. So let me explain it. So the KAN layer apply the learnable nonlinear basis feature to its input feature. This like the learning flexible transformation before the passing them to the sequence model. And the BILSTM layer, this one is read the sequence forward and backward, capturing both past and the future context within the input window. And the extension layer put the hypervisor on the on-time step that constant more useful information. And finally is the full connected layer. It convert those representation into the predict future price. So this is the KAN-BiLSTM is the design to the quick, powerful feature wise nonlinearity and wise directional memories and extension. The second model is more standard Attention-LSTM, and LSTM produce a hidden state at the extreme state, and the attention then the score those hidden state and take the y sum. So this model focus on important time period. And the third model is the BPNN, the fully connected neural network. It doesn't have the sequence structure, but it's good as capturing nonlinear relationships among the selection feature, and it's relatively fast and stable. So for this slide is talking about the optimization. So let me summarize it quickly. So it's generated a set of the candidate solution and gradually for the Pareto form, which you can see for the age of the datasets lower left, and it's better with the low MAPEs and low variance and the hyperparameter of the network, and the optimization are given in the table, but the key idea is the wise are learned, not hand turn, and the complexity threat of the accuracy and the stable. So now let me summarize of the predictions performance in the big table. In the table H in the paper is compare all the model on the 3 dataset. So on the Chinese choice win, the ensemble reach the MAP of the 4.99%, which is better than any single model. And the Chinese corn it's get 4.05%. and the US corn is 7.49%. So the multi-object writing actually translate is the better real prediction for performance. To make the result easier to see, this picture show the 3 of the errors graph, and all 3 port the proposed model is consistently at the or near the lowest bar. And this one they want to explain with the LIME, so they try to answer the question for this particular prediction, what the post the price up or down. They show the feature with the positive or negative contribution. Few pattern in the 3 dataset historical price feature, especially the current time state have the positive impact, and some of the GPO related feature sometimes appear in the red, meaning that when the geopolitical risk is low, the model tend to adjust its focus downwards. LIME look from the outside, and the LRP look from the inside of the network. So I added the picture you can see here, so I will summarize it shortly. So together LIME and LRP give the both local explanation and the global picture of how the information flows through of the network. And the conclusion, the paper proposed and through an explainable forecasting frameworks engineer to select the feature and then the stable of the 3 deep model, matches objective wise optimization, interpretability with the SHAP, LIME and the LRP, and the model achieve the good accuracy and stability on the 3 real future dataset. And then the interpretability tool give the insights that are useful for policymakers and trader, for example, confirming the dominance rule of the historical price and showing how GPO and WTI affect the forecasting focus. So that's all for my presentation. So thank you for watching.